All right. Well, thank you very much. Well, I think needless to say, this is truly a great honor and distinction for me to give this presentation, especially to be the first one. And I think the main message that, of course, I want to convey is the great and huge impact that Egon Ballas had not only on me, but on my students. In fact, the impact was so great for many years that, in fact, as you can see, the name of my website actually has his first name. It's egon.cmu, edu, and it's really for him. So what I want to talk about is global optimization of non-convex, non-linear generalized disjunctive programs. But before I start, I want to explain why the impact that Egon had in chemical engineering, which of course is outside from industrial engineering operations research. When I came here to Carnegie Mellon, I decided to get interested in mixed integer nonlinear programming. And sure enough, I found this paper back in 1971 that Egon had written on MI-NLP, which to my knowledge is perhaps one of the first papers that has been written in that area. But actually, not only me, but also, of course, my students, we greatly benefited from the courses that Egon taught, especially his legendary course on integer programming. And the impact, of course, was also at the level of research. And in particular, I'm listing, listing here those PhD students who actually worked in the area first of mixed integer nonlinear programming and then generalized disjunctive programming. So you can see these 14 students were directly impacted by Egon. And in most of the cases, Egon was actually part of their PhD committee. In fact, Egon was so involved also with chemical engineering that he had actually a courtesy appointment in the Department of Chemical Engineering, and he taught twice two mini courses on disjunctive programming in chemical engineering. So needless to say, you know, he was truly amazing person who had a huge impact in our department, and I would say in chemical engineering by and large. Now, so what do we mean by generalized disjunctive programming? Well, this again was inspired by the work of Egon, his 79 paper on disjunctive programming, defined as linear programming with disjunctions. What we wanted to do here in chemical engineering, we have to deal with nonlinear problems. So essentially the idea here was to the fund to say, well, in addition to having continuous variables, we have discrete variables that we represent as Boolean variables. And the idea then is, of course, you have an objective function. The first term would represent typically the combinatorial part that comes from the disjunctions. Then we have a set of common constraints that have to hold true regardless of the discrete decisions. And then the Boolean variables would be typically included in logic propositions to represent discrete constraints. And then the part of the logic, if you wish, in terms of the continuous variables, was represented through disjunctions, where you can see at each term here, we have a Boolean variable, yjk, that indicates if it's true, then the constraints need to hold true. If it's false, then we disregard it. It's like an if then else type of constraints. And these hold true because, of course, we have a or, exclusive or operator in this problem here. So why did we get interested in a problem like this one? Well, because we clearly saw this as a very nice high-level representation for modeling, because modeling is a major aspect that we do in chemical engineering. But the other one is that because it also gave us a very nice framework for deriving both mixed integer and mixed integer nonlinear programming models, and not only one, but several, and have a better understanding, in particular for the relaxation. And the big challenge here, of course, was the question, well, what do we do when some of the functions involved here in the objective or in the constraints are actually non-convex constraints? Well, to answer that question, of course, and just to illustrate first, you know, with a very simple example, how these problems arise. This is a pooling network design problem, where you can see we have a set of streams, a set of pools, and a set of products that we want to produce. So this problem can actually be formulated in the form of a generalized disjunctive programming problem. The objective function in this case is linear. We have a set of common constraints, which are basically mass balances in terms of the flows. And the two disjunctions, the first one represents whether or not we select a given stream. If we select it, we pay a fixed charge. And the second set of constraints, one of the pooling, deal with the question, if we do select a pool, we need to perform blending operations, and that's where bilinear terms arise. It's the source of non-convexity in the problem. And for example, with the methods that I'll describe, we'll see that we can actually solve such a problem to global optimality and obtain the optimal structure that is shown here in the figure. So again, how you address these problems problems? Well, first, of course, we need to assume convexity. That's the sort of building block for addressing these problems. And here again, the question that my first student, so the first formulation was actually proposed by Ramesh Raman, PhD student of mine, and then Sam Lee followed his work, and we asked a question, how do we construct relaxation for such problems? Well, the easiest form to do that is with a big M reformulation. We replace the constraints that we have in the disjunctions with big M constraints as we have here. And this is done by introducing the 0, 1 variables lambda. Okay, so if lambda is equal 1, we enforce a constraint. If it's 0, then of course it gets relaxed. And exactly one of the lambdas for each disjunction has to be true, because again, it's treated as a exclusive OR. And the relaxation is simply obtained by treating the lambdas as continuous variables between 0 and 1. And therefore, of course, that gives us a way of computing a lower bound to the optimum solution of the generalized disjunctive problem. Again, assuming in this case that we have convexity. But of course, this is not the only way of reformulating the problem. And here again, inspired by the work of Egon, both his seminal paper 74, which was not published, and then later on, the one in 1971, we considered the issue of how do we construct the convex hull for each of the disjunctions. And this, again, can be done, as is shown here, by introducing disaggregated variables, very much again in the spirit that Egon had done for linear constraints, polyhedral constraints. Or here, as you can see, we disaggregate the variable x into variables nu with the upper bound constraints. And one of the issues here, in addition to the condition that the summation of lambda be equal 1, we also have to introduce what is called the perspective function. I should indicate that actually this work, and since he's also here, Sebastian Serio actually worked also on convex disjunctive problems and also sort of came up with a representation for this problem. So the nice thing about having this is we have a set of convex constraints, and if we consider the intersection of the various convex hulls, and we obtain what is called the hull relaxation, as Egon actually denoted that problem. So basically then the whole relaxation problem is shown here, where instead of using the big M constraints, we represent the convex hull for each disjunction, and again we introduce the perspective function. And of course, we obtain a lower bound based on that problem. And again, we can easily prove here that the lower bound predicted by this problem is generally greater or equal than the one predicted by the big M reformulation. The trade-off here being that the big M is small in size but has a weaker bound. The one of the whole relaxation is stronger, but it's of course larger in terms of size. So here, one of the issues that we have to deal with is of course the question of the perspective function. Perspective function has a property that if the function g is convex, then the perspective function is also convex. And the challenge then here in terms of implementation of the algorithms, how do we actually implement such a function? So at the time with my student Nick Sawaya, we developed an approximation that I'm showing here. At first sight, it looks rather complex. It's actually one where if the tolerance epsilon goes to 0, you recover the original perspective function. We're basically multiplying 1 minus epsilon and adding the epsilon to each of the terms. And the interesting property that this approximation has, it is an exact approximation when lambda is equal to 0 and lambda is equal to 1. And that meant that this gave us actually a way to numerically implement the perspective function using nonlinear programming algorithms. In fact, it also has a nice property that if the original function is convex, this approximation function is also convex. Now, of course, things have also changed. I have now a student, David Bernal, who's actually looking into the issue of using conic programming. The idea here is any given convex function can also be represented through the closure of the convex set through the set of equations that I have here coming from conic programming. The advantage that we have here is that in this case, a perspective function can actually be represented in an exact manner and applying again for conic representable functions. The main outcome, if you wish, of using this approach is that we have now, as is shown in the figure, for example, if I have a quadratic constraint, the one I'm showing here, where in the left you have here the feasible region. In the middle, if you don't recognize the second order cone, you get an approximation that is not exactly the same as if you do recognize the second order cone constraint. So this is actually work that we're doing in progress to handle the perspective function. But the question that we asked was the following. Say, well, we have the big M, we have the whole reformulation, can we do any better? And of course, what did we do? Well, of course, in this case, we resorted to Egon. Basically looked at his papers all the way again back from 79, the also 85 paper. But essentially what we did was to extend the disjunctive programming theory that Egon had developed from polyhedra to nonlinear convex sets. So, well, why? Because that's, again, the structure we were essentially looking at here. And the big challenge here, and I remember we had several meetings with Egon trying to discuss, well, how do we relate what we call GDP with disjunctive programming? And the complication here comes from the fact that, again, we have these Boolean variables, and I think these days are often denoted as indicator variables. So how do we relate this to a continuous disjunctive programming problem? Well, very fortunately, my student Xawaya came up with a nice idea of saying, well, what we can do, we introduce these continuous variables lambda ik, and what we're going to do, instead of having the Boolean variable y as the indicator variable, we're going to say lambda is equal 1. If it's true, then of course the constraints hold true. And of course the inequality constraints, for example, in terms of the propositional logic, were represented in the form of linear inequalities. And what is nice here is the fact that when we do this transformation, we can actually show that we can actually guarantee the integrality of the continuous variable lambda, because we have an exclusive OR in the disjunction, only one lambda can be equal 1. And that then means that the discrete continuous generalized disjunctive programming problem is equivalent to a continuous disjunctive programming problem. So I think that was actually sort of the key observation that allowed us to connect to the work of Egon. And Egon basically, as you know, had developed this concept of a regular form, which is represented as an intersection of the union of convex sets. And essentially, again, in his paper of 1985, he had this very nice theorem that basically told you how to go from that representation to the convex whole. And essentially, the idea here is that if F, the regular form, is given, then it can be brought into disjunctive normal form in order to, again, to obtain a convex whole, applying what are called basic steps. Cardinality K is the number of disjunction, and currently K minus 1 is the number of steps that you need in order to reach the disjunctive normal form representation. And essentially then here, what we tried to do was to say, well, given then the results here that we have from Egon, how can we apply that to our problem? Well, obviously, what's interesting in here, our GDP problem, which is the discrete continuous, which is an equivalent to the continuous disjunctive programming problem, can then actually be represented as a convex nonlinear programming problem that is actually equivalent, again, to the original GDP problem. Basically, I'm stating here the theorem that came out from the work of my PhD student, Juan Pablo Ruiz. And essentially, again, the exciting thing was the idea that the GDP problem, at least theoretically, could be represented in the form of a nonlinear programming problem, again, applying the basic steps, taking it all the way to the disjunctive normal form. And that means, again, we can, in essence, very much like in the spirit as is done, for example, in the theory of convex creation of mixed integer linear programming, go from a discrete problem to a continuous problem. And again, I should mention that Sebastian and actually also later Stubbs and Marotta actually obtained very much similar results for obtaining the convex whole of a set of nonlinear convex constraints. So once we had this, well, of course, the issue here, this is a nice theoretical result, but from a practical point of view, it's not really practical to go all the way to the DNF form. Therefore, typically what we had done here was to perform a limited number of basic steps using some basic rules, trying to exploit the structure of the constraints. And here again, resorting, you can see the huge impact of Egon, resulting the formulation I'm showing here. Well, the interesting thing is that when you perform the limited number of basic steps, you can still keep the same number of integer variables that you had in the original problem. So you don't need to introduce new variables because we have the integrality guaranteed here through the variables lambda that are shown here. So having then this idea of the basic steps, then now we do address the question, well, what do we do if the functions are convex? Because everything I presented so far is for convex functions. Well, the idea here that came up was to say, well, we can actually maybe use some of these concepts in order to strengthen the lower bound of the, for obtaining the global optimum for these problems. So the idea here is the following, to say, well, I have a non-convex GDP problem. What we're going to do, we're going to replace the non-convex functions by typically convex envelopes, or in general, under and over estimators of that function. And then we define a convex GDP problem, for which, of course, we have the theory that we have presented. But the interesting part here was to say, well, instead of just solving directly that convex GDP problem, we can actually strengthen that problem with a tight convex GDP precisely with the idea of applying basic steps. In that way, we can then obtain a stronger lower bound. And those of you who are familiar with global optimization, lower bounds are extremely important when you do global optimization, because otherwise these problems, of course, have exponential complexity. And therefore, having a good lower bound, a strong lower bound, is really essential for solving these problems. So basically then, the idea here was to say, again, it's impractical to go all the way to the disjunctive normal form. My student Juan Pablo developed some ideas in terms of some basic rules on how to apply the basic steps. And these could then also be applied in order to derive tighter bounds on the variables, which is another important thing. So what's the consequence here? Well, here I'm showing a set of 10 test problems. The first 5 involve bilinear and concave functions. So that means that the convex envelopes are linear. So basically, the whole relaxation in this case is a linear programming problem. In the case where we have linear, fractional, polynomial, or exponential, the convex envelopes are nonlinear. Therefore, actually, the whole relaxation is a nonlinear programming problem. But the thing that was interesting here, you can see here what's the global optimum, what's the lower bound that you predict with the whole relaxation. Well, if you apply the idea of the basic steps, you can see that actually we can improve the lower bounds. For example, first problem, lower bound is minus 128. We can improve it to minus 1.1. So essentially, we're increasing the lower bounds on average, in this case, by 22%. But what was also very interesting here, in 8 out of the 10 cases, the lower bound that we're obtaining is theoretically the best lower bound because it's actually identical as if we had gone all the way to the disjunctive normal form. Okay, which of course was just simply verified that that was actually the case. So once we have a way of predicting strong lower bounds, what do? Well, basically we then apply global optimization algorithms, basically essentially a tree-search branch and bound type of algorithm, where here what we do, we take the reformulation of the GDP problem. We then also do bound contraction because getting bounds is extremely important for these problems. And then essentially we start with a disjunctive branch and bound where we branch on the Boolean variables. And then when we find a feasible discrete solution, we resort to a spatial branch and bound, meaning we now branch on the continuous variables. So how does this work? Well, you can see here in this table the results for the first problems that involve the bilinear and concave functions basically meant reducing the number of nodes by 44%. For example, the third problem from 13 nodes to only 1 node. The fourth problem for 450 to 1/2 to 227. CPU time is not as large because now, of course, we're dealing with much larger subproblems at each node of the tree. Now, so how do we handle then problems that are larger in terms of size, like industrial type of problems? So here, my student Francisco Tres Palacios developed what is called the logic-based outer approximation, sort of based with the idea that we have, again, lower and upper bounds. Again, don't have, of course, time to explain it in detail, but basically the idea is to make use of cutting planes. In other words, to replace the explicit nonlinear functions of the whole relaxations by cutting planes. And there's also, of course, other details of the problem. So here we have the non-convex GDP problem. Again, if you want to have sort of a geometric view of the problem, so we have non-convexity in the common constraints and non-convexity involved in the terms of the disjunctions. This was a practical problem that actually we addressed. This was joint work with ExxonMobil, Dimitri Papageorgiou, actually a former student of George Nemhaus. This is very much similar to the problem I described initially, except that this is a multi-period model. And essentially here, what we then have, again, we can represent the problem through disjunctions. And the bilinearities arise because of the fact that we have the bilinear terms in the constraints. Now here, again, I don't have time to go through the algorithm, but basically idea is a little bit in the spirit like in the MINLP algorithms. We have a master problem that's making use of these cutting planes from which we then predict the discrete variables. We obtain an upper bound when we're actually maximizing. We then fix a subset of these discrete variables and solve a much smaller non-convex MINLP where we can resort, for example, to codes like Baron for my colleague Nick Sagnidis. Now then, how does this algorithm work? Well, it performed actually quite well, as you can see. This is the average result on 43 instances. And basically, you can see after roughly about 1,000 seconds, we're able to close the gap. With a code like, for example, skip, you can see we get a huge gap even after that time. So it was truly encouraging to see these results and how the results of, that came largely from Egon, were translated to being able to solve such an industrially challenging problem. So with this, let me just finish by saying, well, what I tried to present here is an extension of the disjunctive programming theory that Egon had developed for, did the extension for nonlinear convex sets and showing how we can use hierarchy of relaxations through the concept of basic steps, that the tightest formulation, we can find an equivalent nonlinear programming problem, which I think theoretically is a very nice result, and that the framework can be extended to non-convex GDP problems, as I indicated through the examples, and that the logic-based order approximation, the algorithm I outlined very briefly, at the end allows us to solve large problems because we can obtain tight lower bounds on the global optimum. So with this, needless to say, all this work would have simply not been possible had it not been through the intellectual influence of Egon Ballas. And as you can see here, he left us at the end his very nice book on disjunctive programming that largely summarizes this great work that he did. And again, Egon was truly a scholar, an intellectual giant in integer programming and disjunctive programming. So I'm absolutely most grateful to him and the whole community of chemical engineering. Thank you very much.
Do you have time for questions? There are any. I have one question myself.
Yes, sir.
Can you describe the auto-approximation for non-convex problems? You did proof optimality, so I assume there's also an auto-search procedure.
Right.
What kind of search do you use there?
For the, you mean the, yeah, so basically the idea is that, again, we start with a non-convex problem in which we replace the non-convexities by convex envelopes. In that sense, we have guaranteed lower bound. Mm-hmm. And essentially, the proof of convergence comes from the fact that the lower bound that we're obtaining is a rigorous lower bound. That's basically the whole idea. And basically, again, I didn't have time to go through the details of the algorithm. We accumulate enough of these outer approximations. We have actually a special procedure that gives us, again, the best, if you wish, cutting plane, the tightest cutting plane that is valid for a non-convex region. That's basically sort of the key. But again, it's described in the paper. Okay. Okay? All right.
Any other questions?
It's too early. Yeah. Okay.